And the next talk is by Gabriel TOBIE about Titan's deep ocean evolution and evidence or not for its presence.
Thank you, CB. So good morning, everybody. So I will try in this talk to give an overview of what we know, or more, what we don't know regarding the ocean, the deep ocean of Titan. So as you know, we got some evidence from Cassini and from Huygens, but you will see during the duration of the mission, some evidence disappeared, some others appears, and it's what I will try to present you today. So let's start from before Cassini Huygens. So the idea of oceans in the interior of Titan is not new. It's something that was already proposed by several papers, several theoretical papers already in the 70s and 80s. So it was mostly for large moons, so not only Titan, but also the moons of Jupiter. So here I'm just highlighting two seminal papers. The first one dedicated to Titan. So it was done by Jonathan Lunin and Dave Stevenson, where in this first model, they show that it will be possible to explain the release of methane by the destabilization of methane clatrate during the evolution of Titan, and mostly during the early stage of its evolutions. So it was one first hint that indicate that we may have a reservoir of clatrate and methane, and at the same time, we may have an oceans in the deep interior, but still not fully sure at that time if the ocean may survive until present. So then there was another series of papers, and the last one that I will mention here is the one done by Grasset, Sautin, and Deschamps, which was done in Nantes universities. And it was exactly released at the time where I start to work on these topics. So I start my journey to Titan and to Titan and the other moons of the Saturn system in 2000. And in this paper, they show clearly that the long-term survival of a subsurface ocean may be possible. And this was also supported by the fact that at this time, we have detection of ocean in the Galilean moons. So there was no reason that Titan will not have an ocean. And especially in case of Titan, we expect that there was some kind of ammonia, and the presence of ammonia will help the survival of these oceans. But in the case of Titan, there is another issue, which is very different from the Galilean system. In the Galilean system, we know that Europa, Ganymede, and Io are trapped in the Laplace resonance, and this helps maintaining a relatively non-zero eccentricity, which is a driver of the long-term evolution of these bodies. In the case of Titan, which was already highlighted first by Dermot and Sagan in the 80s, that there is a problem with the eccentricity of Titan, because Titan is a big body and has a large eccentricity. And this eccentricity, this orbital eccentricity, should decay as a function of time due to tidal friction. So if there is a global methane ocean at the surface, this would reduce the eccentricity. We know that there is not a global ocean, so there is not an issue. But if there is an ocean in the deep interiors, and if the interior is warm enough, we should also generate significant dissipation. So the eccentricity should decrease. So this was highlighted by this work of Frank Sol and Sears and Ralph Lawrence, where they show that at present day, the fact that there is a large eccentricity of Titan, this implies that either the interior is rigid and cold and there was no ocean, or there is another mechanism that can explain the eccentricity, which is unknown at present. So this was the debate at this time. And then based on these two observable, I first built the first model. So that's why I want to show this just before we go in more detail about the ocean, the evidence for the ocean. But I tried to reconcile these two aspects, the long-term survival of the ocean and the existence of the eccentricity. And by coupling the eccentricity evolution and the crystallization of the ocean, in fact, we show that in this first study that it was possible to expand the current eccentricity of Titan if Titan remained in a conductive state during most of these evolutions, which means if the ice shell is relatively thin and the ocean is not very deep, which was very exciting also because it means that the ocean is close to the surface, so they may have exchange. And this indicates that we need onset of convection relatively late during the evolution of Titans. So it seems that it will be possible to reconcile the presence of an ocean and the high eccentricity. So it was just at the time where we got the first data. So now we have the data and we can try to test these ideas and these hypotheses. And the first very important data that was provided by Huygens, which was already presented yesterday and the day before, it was the fact that the GCMS on Huygens detect argon-40. And this is probably the main, I think for the interior, to constrain the interior's evolution of Titan, is probably the main data, the most interesting data. Because this clearly indicates that if we have argon-40, we know that it's come from potassium-40 in the silicate part. So this clearly indicates there is an exchange between the rocky core and the atmosphere of Titan. So this clearly indicates there is outgas, at least at some point during the evolution of Titan. Another very important aspect thing is the fact that the isotopic ratio in carbon is relatively close to Earth's ratio, so to the standard ratio. And this also indicates that the methane we see on Titan today should not be too old. It should be relatively recent. So that was the first clear information we got from Huygens regarding interior. And another unexpected also result was the fact that during the Huygens descent, there was a detection of electric perturbation. And as I will show you after, it was first interpreted as an ocean, indication of ocean, but now this is questions. So just after, so Jonathan already showed that yesterday, but just after the landing of Huygens, then we tried to incorporate also this latest detection of argon and methane to build an evolution scenario that may reconcile the different constraints we have at that time. So we proposed this model with Jonathan and Christophe, where we predict that the release of methane may be controlled by the cooling of the ocean and the onset of convection relatively late during the evolution of Titan that may generate the last release of methane. And we give some prediction regarding the ice shell thickness, the love number. So if there is the love number is about 0.3, we should have a clear detection of an ocean. And this is wrong. In fact, we predict in the other direction. But so it's the moment of inertia. So that was a prediction. So now we can see if the Cassini and Huygens data can be used to test this kind of ideas. Of course, this is not the only evolution model that was proposed. I just highlighted this one, but there is other studies. So let's go back with this first indication. So the first hint of a potential water, deep water ocean on Cassini, on Titan was provided by Huygens. So from this detection of electric perturbation during the Huygens descent. So you have the data here, the electric field as a function of altitude, and we see clearly there is a change in the electric field. So this was proposed by Christian Béguin and co-author. They tried to explain this increase of electric field as a consequence of a Schumann-like resonance. So it's a resonance of low electric waves, low frequency electric waves between two conducting layers. So the upper layer will be the ionosphere, and the lower layer will be another conductive layer. And they propose that this layer may be an ocean. So they predict that the ocean should be between 50 and 80 kilometers. So it's still not clear to me if they predict that because they can really say from the data, or it's just because we predict in a thermal evolution model that should be between 50 and 80 kilometers. So I don't know. But more recently, Ralph Laurenz and Alice Le Gall reanalyzed this data, and they show that this maybe the interpretation may be wrong. Because in fact, when we look at the variation of the electric field measured by Huygens, it seems that there is some kind of correlation with the parachute deployment. So maybe it's not real. So we cannot be fully sure that this measurement is a proof of a conducting layer at depth. So this will be tested in the future with Dragonfly. For the moment, just we have to stay with that. The second evidence that was provided, so again, with Ralph Laurenz again here, it was based on the radar measurement. So from the radar, there was a prediction, observation of a drift, so a change of the length of day of Titan, which was suggesting that there will be, due to the forcing of the atmosphere, this implied that we should have an ice shell which will be decoupled from the deep interiors. So this was interpreted as a proof of an ocean. And what was interesting with that is that the fact that this change of rotation will imply not only that there is an ocean, but that the ice shell is soft enough to readapt to the new shape forced by the atmosphere. So it seems very interesting. So it was a great result, but then 2 years later, Stills et al. Show that in fact, the radar measurement was not correct and there is no significant change of the length of day. Which means that there is no proof of an ocean based on that, which is too bad. But fortunately, the same data from radar can be used to constrain the obliquity of Titan, and this indicates another hint for an oceans. So the radar confirmed the obliquity of Titan to be 0.3, and the 0.3, which seems degree, which seems very small, in fact, is 3 times larger than what was expected for solid interiors in the Cassini state. And this was proposed by Rosemary Ballon and collaborator. She proposed that to explain this obliquity of 0.3, we need again a decoupling of the outer ice shells from the deep interiors, which implies a low viscosity layer or liquid layer, so that it works with the oceans. And she predicts, so some work we did together, we tried to predict what should be the ice shell thickness and the moment of inertia that may explain this decoupling. And it seems that there is some solution that where we can predict an ice shell thickness, again, between 50 and 100 kilometers, seems to work. And, and then we can explain the obliquity, but we predict a moment of inertia which is relatively small, smaller than what was measured by Cassini, which was indicated here. So this, again, seems to indicate an ocean, but it's not a clear, fully clear evidence. And finally, sorry. The last evidence that was for me the most convincing one was the measurements of the tidal deformation of Titan. So this was already planned. I think it was the only evidence that was already planned to be detected by Cassini. So for that, we need to do detailed gravity measurements. So it's what was presented by Daniele Durante yesterday. So thanks to, I think there was about 10 flybys dedicated to gravity measurement, and some of them was relatively close. So from that, we can derive, so here you have the geometry of the flyby. You can see that it's not perfect, but at least we have some distribution of the flybys. And by monitoring, determine the static field properly, and then we can monitor the change of the gravity field. And from the change of the gravity field, we can infer this love number, which quantified the contribution of the tidal deformation to the gravity field. So this was first determined by Yes et al. 2012, and then this analysis has been confirmed by Durante et al. By improving the model and the data and incorporated more flybys. So we got this value, 0.61, which was okay, it's good. It's larger than 0.3, so it clearly demonstrates there is an ocean. So then we did some work, so this with Giuseppe Mitri, we tried to see what we can say regarding the ocean, the depth of the ocean and the density, and we see that, okay, we can explain the ocean for an ice shell between 50 kilometers and 100 kilometers if the ocean is between this density 1.15 and 1.25, which indicates a relatively dense ocean, which implies significant salts. Okay, we predict that, we were happy. We were still not expected to have such a high K2, but seems possible. And then, more recently, another group, Gersens et al., reanalyzed the same data using the same track, the same gravity data, but with a different approach. And they end up with this K2 value, which is like about half of the value that was predicted. So you can see here, maybe you cannot see, but I plot here the difference of gravity solution between the two. You will see there is almost no difference. The only difference is only on this arc. In this region where Daniele showed yesterday, there is a very good constraint, there is almost no difference. So the difference is only in a few arcs. So that's why because the tidal signal is very weak. So we should be careful, but we have this new value. And if we take this new value, then the ocean of Titan is not dense. It should be a low density ocean, and it's consistent with the ammonia water ocean, which was predicted by Sol et al. So I just checked yesterday, just predict this curve. And we can see that for 65, so it's very precise kilometers, we can get the K2 value if we put 5% of ammonia, which is just an example, but you can see that we can expect. So there is still this debate last year, and then another debate arises just this year. A new constraint comes, this time not from the gravity measurement, but for the interpretation of the spin state of Titan. So in this paper by Downey and Nemo, they show that by interpreting the speed state of Titan, they can constrain the dissipation inside Titan. So this time it's not the K2 that we measure, but it's the K2 over Q. And this K2 over Q value is very high. It was not expected to be that high. So this implies that there is a very strong dissipation inside. And if we go back to the prediction of Rappaport et al. 2008, where she first, in this paper, they first predicted what should be the K2 value and what we can say. They clearly said that if this dissipation is very high, we may have solution that could mimic a very high love number and without an ocean. So it's what we can see here. So sorry, maybe you do not see the line. But this line is a prediction for the imaginary part, so the K2 over Q, as a function of the viscosity of the deep ice layer on Titan. And this is the K2 value. So this is the value by Durante. This is the value by Gussens. You can see that both can be explained with the solid models. And then it really depends on the imaginary part. So it seems that we may have a solution where we can have both. We can explain also the K2, which is very large, without an ocean, which is problematic. So this is where we are right now. So there is a recent study that will come soon that will additionally provide some indication on the K2 and the imaginary part, but I will not mention it today. But what this implies, if the K2 over Q, so the dissipation is very high, this has a very strong implication for the evolution of Titan. Because this implies that the power generated inside is very large, 2 to 4 terawatts. So maybe for you it's not large, but it's 2 to 3 times what we expect on Europa. And everybody agree that Europa is a very active moon. So it's very strange. It doesn't seem to be consistent with geology, but maybe there is something we don't understand. Another implication also is it's a rapid damping of the eccentricity, which means that in less than 70 million years, the eccentricity should go down to 0. So either the eccentricity was larger in the recent past, which implied that the power that was generated is even bigger. It could be 10 terawatt, 20 terawatt. Maybe it's possible. That's a possibility. Another very surprising observation was provided by this time by monitoring the astrometric, from astrometric measurement, the position of the moons, and by Lene et al. They show that the dissipation in Saturn may be very large, which means that the moon should expand their orbit very fast. So if we look at the prediction, Titan 1 million years ago was not here, it was here. And if it was here, the dissipation will be much larger. So this clearly indicates that maybe something very strange is happening in Titan at present. And even if we have a lot of good data, we still have many eccentricities. So we need to wait now the future, and we need to wait for Dragonfly to maybe bring some additional measurements. So I will not have time to go in details. I guess ZB will detail Dragonfly, but just to mention that for the interiors, Dragonfly will provide several keys measurement that will be complementary to the measurement that was done by Cassini. There will be, of course, the seismic investigation that will maybe directly detect the ocean, if there is an ocean. There is electromagnetic sounding that will test this electric perturbation in a more detailed way. The rotational parameter will be also more precisely determined. And the last thing that I wanted to mention is the pressure measurement, which was maybe not expected initially, but from precise pressure measurement, we may have an additional constraint on the tidal deformation. So it was some work we did with Benjamin Charnet. And yes, that's a possibility. And just last but not least, which will be mentioned later, you know that there is a project to go back to the Saturnian system for ESA. So the main target is on Enceladus. But we will fly over Titan, and for sure, if we fly over Titan, we need to do gravity measurement as it was done by Cassini. And if we add additional flyby, maybe we have a better constraint data. Okay. So thank you.
Thank you, Gabriel. Are there any quick questions? I didn't see any online. Jonathan?
So it seems to me that the enduring theme among all these models is that it's very hard to preserve Titan's orbital eccentricity over geologic time, which is very interesting. Ocean or no ocean? The one point about the Huygens probe observation, electric field observations, leaving aside that they may in fact just be reflecting parachute deployment, is that the 60 kilometers comes from the fact that the electric field measured at the surface was non-zero, but there was a gradient, and they then took that gradient and they continued it down below the surface to where the field would go to zero, and they argued that that was where you had the conductor and that was where the ocean was. So I think, as I recall the paper, there was a real argument for the 50 to 100 kilometers.
Yeah, but I
Again,
think an
leaving
argument.
aside the validity of the data.
Yeah. But maybe, yeah, Ralph will better explain to that than me. But if I understood well the paper he did with Alice, they show also that after the landing, the electric field strongly reduced. So if there will be a continuous increase with depth, it should not stop at the landing. So I think it was one of the arguments, if I understood well the study data. But you should remember it's a single point. So that's why if we have other measurements with Dragonfly several times, if we observe several times this effect, then it will be more.
Yep.
Yes, yes. And when this paper was the first paper, and the paper by Began was the first one to really show that there is a detection of the ocean, which was great.
Thank you very much, Gabriel.